So today we are going to look at inverses again. We did this in Chapter 7 with logarithms and exponential functions. But we're going to determine whether the inverse of a function is a function, first of all, which is pretty basic because that's just going to be, we use the vertical line test for telling whether something was a function. We're going to use the horizontal line test to tell whether the inverse is a function. And we're going to write rules for inverses of functions. And then we're also going to use composition today also with like what we did the other day. So if you remember from earlier, we talked about whether something is a function or not, and we used the vertical line test for that. And so if we want to tell whether the inverse is a function, we use what's called the horizontal line test. So if a horizontal line intersects more than one point, then the inverse of that function is not going to be a function. So basically it works out this way. If the function is always increasing or always decreasing, the inverse will be a function. If the function has any max, min values, turning points, okay, then anytime it goes up, comes back down, goes up again, or goes up and comes back down, because we have a spot where there's a turning point, then the inverse is not a function because, as you can see from this picture, it fails the horizontal line test. All right, so we have these two graphs here, this blue one and the red one. All right, let's look at the blue one first. The blue graph. All right. So if I draw a horizontal line on here, and I slide that horizontal line up and down, it never intersects the blue line in more than one spot. So with the blue line, the inverse is a function. Because if I took this graph and I rotated it, we can see that blue line would pass the vertical line test. Right? We'd never have an intersection. Right? The red line, though, right? The red line here, we've got a few spots where the horizontal line test fails. So the red line, the inverse is not a function. All right, just because it fails the horizontal line test. All right. So would the inverse of this be a function? Yes, because it passes the horizontal line test. Okay. I bring down that horizontal line. All right, it's never going to intersect anywhere but one spot. So the inverse of that would be a function. Okay. All right, there's the first thing. All right, we like them when they're that hard. Okay. All right, so if we recall from lesson 7.2, we learned how to write the inverses of functions. And we learned that we can exchange x and y and just solve our equation for y. So here they want us to find the inverse of f of x equals the cube root of x plus 1. So the first thing we want to do is determine whether it is a function. And we're also going to state its domain and range. Right? So first thing we want to do is we want to graph the function to make sure that the inverse is a function. So go ahead and let's graph this on our calculator first of all. Cube root of x plus 1. So cube root is under math, number 4. X plus 1. Right. And we'll graph that in our standard viewing window Zoom 6. And we get this graph here. Right. Cube root of x plus 1. All right, so we look at that. Okay, does that pass the horizontal line test? Okay, so the inverse is a function. All right, and let's do domain and range then, before we actually find the inverse. All right, so when we look at this graph here, right, and so the domain for this graph, does this graph ever stop going from left to right? No. So the domain is all real numbers. Okay. Is this graph ever going to stop rising? So, or falling. So is it ever going to stop going up or down? So this graph, even though we don't see much of it, that if we expanded it, then it would just keep falling and falling and falling, going to the left, and keep rising, going to the right. You know, which means so then the range would be all real numbers also. Okay, that makes it nice. So just remember then, when you find the domain and range of the inverse, we switch them. All right. The domain for the inverse is the range of the function, and vice versa, but in this case, these are both going to be all real numbers. All right, so we want to find the inverse. So we're going to switch x and y. So we'll rewrite it as x equals the cube root of y plus 1. And for the most part, okay, most of the time, if the inverse is a function, then you're almost always going to have domain and range as all real numbers. At least one of them probably will be, if not both of them. All right. So what do I do to solve this for y? How do we get rid of the cube root and the 1? Which one do we do first? Okay, we want to get rid of the cube root. So we're going to raise both sides to the third power. And we subtract 1 from both sides, and we get x cubed minus 1 is equal to. Now, how do I write it when it's the inverse is a function? All right, we're not going to put y equals, we're going to put f inverse of x. Remember, put that little negative 1 up there. All right. So if it's a function, okay, then we have to say f inverse of x equals that. All right. So, all right, because it's a function, right? If it's not a function, then it's just going to be y equals. Okay. So if it's a function, we put f inverse of x. If it's not a function, then we just write it as y equals. All right, so do number 2 down here then. Here, check it out. All right, so we've seen that inverses of functions are not necessarily functions. When both a relation and its inverse are functions, the relation is called one-to-one. So it's a one-to-one function. So those two functions we just looked at here, with the cube root and the cube, those are called one-to-one because the function and the inverse were both functions. Okay, anytime they happen. So if it's a graph where it's always increasing or always decreasing, then it's a one-to-one function. Okay, because for every value of x, there's one value of y, and for every value of y, there's one value of x. So the domain and range of those two are always all real numbers. So we're going to use composition to determine whether a couple functions are inverses or not. All right. So we worked with composition on Friday, so we'll do that. So we want to tell whether these two are inverses. So that means we're going to do f of g of x, and we're going to do g of f of x. All right? And when we're all done with them, if they equal x, then they are inverses. Now, if just one of them doesn't equal x, then you're done. Okay, it's kind of like checking to see if a point works for two different equations. Okay. So remember, f of g of x means we're going to take and we're going to put g of x in for x and f of x. So we're going to take this and we're going to put in there for that x, and then we're going to simplify it. So we get 3 times 1/3 x plus 1 minus 1. Yeah, I'm going to erase this and move it. All right, so we're going to simplify this. So 3 times 1/3 x is x, that's good. 3 times 1 is 3, so plus 3, then minus 1. So this equals x plus 2. Since that is not equal to x, then these are not inverses. So we're using composition. So let's do it the other way just to verify the other way. You don't have to do it both to prove that it's not, but you do have to do it both ways to show that it is. So if we do g of f of x, gives us 1/3 times 3x minus 1 plus 1. All right, we're just replacing x with the other function. So 1/3 times 3x is x minus 1/3 plus 1. So that's x plus 2/3. But once again, that's not equal to x. All right, so I'm just using them to determine whether they are inverses or not. But they must equal x. They must equal x for them to be inverses. Right? So when I simplify them. But if one of them works, I have to test the other one. But if one of them doesn't work, I don't have to do the other one. All right? It's already shown that it doesn't, it's not an inverse. All right? Oops. All right, so you go ahead and just do 3a. Use composition to see if those are inverses. So, 3 simple things. Horizontal line test to check whether a function, whether the inverse is a function or not. Finding inverses just by switching x and y. Just remember that if it is a function, that we write f inverse of x. If it's not a function, then we're going to leave it as y equals. And using composition to tell whether inverses, two functions are inverses or not. Okay? And that's it for today.